Est-ce que le son marche sur la caméra? Ça fait des petits machins, etc. Ok. Et si je vais... Et là, ça marche toujours? Ça marche?
Très bien.
Ok, très bien. Okay, all right. Sorry for the delay. So I'm just going to give a general presentation of Tezos. There's going to be a more specific presentation about different aspects of the project and the code base. But I just want to give you a general overview of what the project is and what problem it's trying to solve and how it's trying to solve it. And I think I have 2 hours, so I'm going to try to keep you awake for these 2 hours and leave some time at the end for questions, because it's always better, because you know what you don't know. I don't know what you don't know, so it's better if you ask me directly. Okay, so I'm going to try this clicker. My hopes are low. Okay, so that doesn't work. That seems to work. Okay. That's just a table of content that doesn't fit in the Beamer slide. All right, so I'm going to start with money, because these things are cryptocurrencies. Cryptocurrencies try to be money, and I'm going to give you a quick historical and theoretical perspective on money. So first, the role of money. And so classically in economics, you give 3 different roles to money. One is a store of value. You would like money to maintain value over time, right? So you want to be able to save for future consumption. You have money now, you don't want to spend it right away. You want to spend it next year, and next year you still want it to have value. So that's a store of value aspect. The other one is a mean of exchange. So you have a can of tomato soup, and I have some money, and I pay you, and you pay me the can. And so that's slightly different, but it's also tied. You know, it's a store of value. Why does it store value? Well, because I will be able to use it to buy goods. So that's a mean of exchange aspect of money. And the third one is unit of account. So you can price things in money. You can enter contracts. You can have wages. You can have prices. It's a convenient way of expressing menus, expressing, if you have a shop, you want to be able to tell to people what you're going to get in exchange for these goods. But it's also enabled economic calculation, right? If you say, well, it's going to cost me this much to do this and that much to do this, you can compare these numbers. And so having just a single scale on which you can compare things makes things easier. So those are traditionally the 3 roles of money. Why do we need money? And that's a question. That's a good question. Well, typically it's because we want to maximize optionality. So let's say I have a bunch of fish. This works. I have a bunch of fish, and I don't know what I want. I have fish today. In the future, maybe I will want to buy a house for my fish, or a steak, or a banana. In this case, so I don't know what I want, and I don't know what I will want in the future, but if I just keep my fish is just going to rot and it will not be good. And so the trick is I will exchange my fish for money, and then I will be able to exchange my fish for a house, my money for a house, or for a steak, or for a banana. Now you might say, why not just exchange my fish for a house, and then I can always exchange a house for a steak or for a banana at a later point if I change my mind. And the idea is you want to get the good which is going to be easiest to buy all this other stuff with, right? And one of them is going to be money. And money is the obvious choice because it will be easier to buy your house with money than with steak. It will be easier to buy your steak with money. So you can think of it as routing in a graph of barter. So a little bit of history. I'm not going to go into the dates. I mostly just want to show the evolution of the concept of money. So first you have barter, and barter works if you have a complete graph. So I have fish, and I can trade it for bananas, or for steak, or for houses. So you can exchange everything for anything. And the problem with that is you need a coincidence of needs or wants. So if I have fish and I want steak, and the person who has steak doesn't actually want fish, maybe what they want is a house, then I can't get my steak. we need to go and find a third person who has a house and do like a triangular trade. It's complicated to route around this graph because not all the edges are present. And so the solution to that problem, as I was saying, is you introduce commodity money. So for example, seashells. And seashells, maybe you start with pretty seashells. They don't really have a whole lot of value by themselves, but they become a convention. You say, I'll exchange my fish for seashell, and then I'll exchange my seashell for steak. So what you lose is that now you have to do at least 2 hops in your graph instead of 1 hop. You will have to just take a hop through the hub. But the benefit is that everyone goes through the hub, so you no longer have a problem of coincidence of needs and wants, because anyone who has steaks and doesn't want it is going to want seashells. Anyone who has fish and doesn't want it is going to want seashells. So you can route your trade in a very, very efficient way, and it's really hard to come up with a graph that's more optimal than this for making trade. So that's the origin of commodity money. I put a seashell here because I made these slides with emojis, and there's no emoji for gold, but also, obviously historically gold has been an important source of commodity money well until the 1970s, in fact. So then you have banking and credits. So the idea of banking and credits is to reduce the need for money. So let's say, for example, you have steak and I have fish, and we don't really have money right now, but we have prices, right? There's already money in the system, so we have some idea of how much your fish is worth and how much my steak is worth. So instead of that, I'll say I'll pay you in the future, and then maybe we do another trade, and then the credit just washes off. So it's a way of making trade without needing money. But the trick is that for it to work, you need to have money. So you can expand, in some sense, the money supply by using credits. The benefit is that so you reduce the need for money. It's faster. You don't need to actually exchange the money. It's safer because no one can come in and take the money. The credit is in your name. And it facilitates long-distance trade, right? If you want to go, you're in Europe and you want to go buy spices in India, well, you can have your boat and you fill it with bullion, and now you have to deal with pirates, or you have to deal with, if you go by land, with robbers. Whereas if you have something like a banking system where you will say, okay, I will put my money in the bank, you will put your money in a bank, and the banks will have credit relationship with one another, you can send money at very long distances without actually having to move the money. So that's very safe, that's a big benefit. There are problems with it, which is that, so your credit system could be based on reputation. So I have a reputation of being a good creditor, I pay back my debts. So that's great, but that doesn't really scale. How does it work if it works in a small village? In a very large economy, if someone doesn't have any reputation and they don't have access to credit, then that can be that can be a problem for them. They can't prove that they would be good creditors. If you end up only lending money to people that you've lent money before, it's kind of circular and can leave people out of the economic system. The other one is that another way of enforcing credit is by force. So if you don't pay your debts, maybe you go to prison, or maybe your assets are seized or something like that. But this type of enforcement is going to favor very large power structure, like very large nation-state governments who can actually enforce those rules. Those are some of the downsides of banking and credits. So fiat money, so that's both old and new. You had fiat money in China in 1080. So it's basically paper money. So it's not based on commodity. It's based on the realization that really what we're doing with this money, we're just keeping track. I'm keeping track of how many fish I gave. I'm keeping track of how many steaks I got. And if you're just going to keep track of something, there's no reason that your money itself needs to be worth anything. So it's like, it's like seashells. And the world has been running on fiat money since basically 1971, when the US severed the link between gold and the US dollar. So why is it that fiat is valuable? And you've had different explanations. One is legal tender laws. So the government goes and say, you have to accept this as money. But on the other hand, they don't prevent you from accepting something else. Taxation, so that's the theory of chartelism. So the idea is that I want to own fiat money because at the end of the year, I need to pay my taxes. I need to pay my taxes in money, so I will have to hold some. So that's one of the reasons. But really the main reason I think is that it's common knowledge that it's money. Just because if everyone knows that it's money, if we're all routing all our trade through this graph, just because we all know that and then the structure, that makes it work. And a really nice historical experiment is one of the Iraqi Swiss dinar. So Saddam Hussein, they used to have their dinar prints by a company in Switzerland, and they would have these beautiful Iraqi dinars. And at some point, Switzerland decided to stop printing those dinars because, even though it was Switzerland, they were reluctant at some point to keep being associated with Saddam Hussein. And so they printed other ones with paper from China, and it was a crappier quality. And so they had these two bills in circulation, but it was the same money. And then at some point, Saddam Hussein had a great idea, because most of these Swiss dinars, they were actually in the hand of bankers in Jordan, which he did not like. And so he said, okay, we're going to remove the old bills from circulation. They will only be the new bills. However, so you will go to the bank and you can exchange your old bills for the new bills. And you will have 1 week to do it. And during that 1 week, I'm going to close the border. So he ended up just like closing it, and then the old ones were not accepted. However, in Kurdistan, people were still using the Swiss dinar. And they were still trading. And in fact, because the Iraqi central bank was inflating a lot the new ones, and these ones, no one was printing them anymore, they started becoming more valuable. So you had a fiat currency issued by a government that no government recognized, but people were still using them because it worked for them. And so when, I'll talk about when Bitcoin came around the corner, a lot of people said, well, how can this thing have any value? Why would it have any value? It's not gold, it's not buy by government. If enough people believe it has value and they start forming common knowledge that it has value, this thing can build value. Okay, so electronic money. So now that you have fiat money, that really represents just, in some sense, some sort of balance. You can put that on some electronic ledger. Most money today is electronic money. It's not Bitcoin. Just like the regular money you have in your bank accounts is electronic money. This is a graph from the Federal Reserve. So what you have in purple here is a currency in circulation. So that's the actual coins, the actual bills, like physical cash. And the monetary base that you have here in blue includes also all the bank accounts. So you can see here around 2008 they started like creating a lot of money in the banking system, not necessarily in a coinage. And then you have the M2, which also dwarfs that, which includes other things such as short-term bonds, money market deposits, this type of stuff. Okay, so all of this money is essentially electronic, the vast majority of it. All right, e-cash. So the idea of e-cash, which started becoming popular in the 90s, late 90s, is we would like to have electronic money, but that's not banking money, like something closer to cash, with these properties that you don't have to trust a third party, so it's not based on credits. I have it, I give it to you, now you have it. Just like cash, but electronically. So not based on credits, and also potentially private. In a cash transaction, I make a cash transaction with you that just involves the two of us. Whereas if I do it through the banking systems, then it involves a whole slew of actors. Okay, so cryptocurrencies are going to be with the first realization of eCash. I'm going to speak a little bit to their design and some of the problems that they faced initially. Motivation. Sorry, I'm going to repeat myself a little bit here. So motivation for cryptocurrencies, protection against debasement. So there's a lot of countries where the population was ruined by hyperinflation. Not a lot, but a few. There's, of course, famous example of Germany after World War I. I think this is Somaliland. And recently, the government of Somaliland so there's been a lot of inflation, also a lot of counterfeits. The government of Somaliland recently introduced a new currency, and they're accepting all deposits, including the fake ones. You can bring your fake one to the... And the trick is because it's worth less than the paper it's printed on, so you cannot make money by printing more fake ones and bringing it to them. So, being protected against that is certainly valuable. It seems to be less of a problem now in developed countries which have developed independent central banks and more protections against that. Censorship resistance. So today, if you use your money, you need to have someone's permission to use your money. And that can be potentially problematic if you're a political dissident, for example. You might want to be able to use your money without asking permission from your government in the first place. Disintermediation. So right now, again, to use your money, you need to have someone there. That person may be charging you money for doing it. They may be disagreeing with how you're spending the money. They may be spying on you. And convenience. There's something beautiful about cryptocurrencies today is that it crosses borders. Really, you cannot, you can use Bitcoin pretty much anywhere in the world, even if it's not very popular. At least if I get money from Cambodia, I can probably only use it in Cambodia. If I get Bitcoin, I will find a few people, but they will be everywhere around the world that can use it. It's programmable. You can program your money. You can do things with it without having access to an API and having people force you to register for a key or even cut you out of their API. And it's predictable. The nice thing is that you know what the rules are from the get-go, and you know exactly. You can tell a little bit what will happen when you program it. So that's some of the benefits. A big one is privacy. With one caveat. So why would you have privacy? Protect political dissidents, protect against discrimination. So, imagine that a typical example was that there was this story about a father who learned on Facebook that his daughter was pregnant because of the ads that he was being showed based on his IP. And you learn a lot of things from this type of stuff that you buy in a store. And right now you're giving all of this data to your bank because your transactions are not private, and so you can potentially be discriminated against based on your purchases. And also protect individual expression. There's a lot of things that we do in public life and that we do in private lives that are different. There's things that I might say to a close circle of friends that I not necessarily would broadcast to the entire world. And you can be more genuine and more authentic when you are allowed to have private thoughts. And if you're not allowed to have any private transaction and economic activity, then I think that curtails economic individual expression. If you imagine that everything you buy when you go to a supermarket is going to be broadcasted to the entire world, you might feel different. You might say, well, I feel bad about getting another dozen donuts. If you look at China now, is starting to have like a credit score system for its citizens, and that gives you access to credit, gives you access to different benefits, and it's based on stuff like this. You overeat, you buy too much things, you buy alcohol, for example, in the supermarkets, and your credit goes down. So privacy is important, with a big caveat that the most popular systems today, like Bitcoin, are not private. They're actually very, very public. As we'll see, privacy is very difficult to achieve, but it is achievable in those systems. Okay, design. How do we build these things? Okay, so the first building block is digital signatures. So digital signatures are a piece of cryptography introduced in the 17th and 18th, and it basically provides these three properties. Authentication. So I have a message, I produce a signature for that message, that's a string of bits, and that authentifies me. I'm the only one who could have been making that signature. It's me. Integrity. It means the message was not modified. So not only am I the only one who could have signed this, but also I signed this message and not any other message. And non-repudiation, which means I can't go out at a later point and say, oh, actually, I didn't sign it. So it's a proof to everyone else that I signed it. I can't go out and say I didn't. And that's a really, really big building block that came after encryption. And the idea is that you can authorize transactions with digital signatures. It's not based on your identity anymore. You can have a piece of information that proves that you wanted to do something because you hold a certain secret. So that's a very, very powerful primitive. And when you have digital signatures, you might think, okay, that's all we need. We can do eCash. And not so fast. So the problem you have immediately if you try to design an eCash system with a signature is you're going to run into the double spend problem. So you have Mallory here, and she's going to sign a check to Alice, and so she sends her signature and says, okay, you know what, I'm sending you some cash. Here's a signature. But immediately she also does the same thing to Bob. And the problem is that how does Bob know that the check is provisioned? You know, even if we had a system where we knew that Mallory has a certain amount of money, like if she sends it both at the same time to Alice and Bob, they don't really have a good way of knowing who really got the money. And the problem is that we're in a realm of mathematics and equational reasoning, and in this realm there's no scarcity, right? I have a value x, I can have as many value x's as I want. It's just information. Information can be duplicated infinitely. And here we're trying to do something which has scarcity. We want to represent only, Mallory has a finite amount of money, not an infinite amount of money. And so equational reasoning gets hard with this type of problems. So one solution is timestamping. So you could use a timestamping service. And so the way it would work is, so Alice signs a check to Bob, and then she sends it to a timestamper service, and the timestamper is trusted, and he says, okay, I see that you signed a check to Bob, and here's a signature attesting that you made that check at this time. And so now if we have a single timestamping service, we'll have a way of knowing which check came first, the one to Alice, the one to Alice or the one to Bob. But the problem is Bob still doesn't know if they're in previous signatures. So I get a check and I say, okay, this check is dated from now. How do I know that there doesn't exist a check signed previously from that person? And so the last piece we need is we need publication. Essentially, is a way we're going to know that there were no transactions before that, is that we're going to publish all transactions publicly. And if all the transactions are visible publicly, then I can look through all the transactions, see that you never made this transaction, and accept it. So they call it Bulletin Board in cryptography papers, and because it works exactly like a bulletin board. Imagine a website that everyone can access, where everyone can put information, and when you can just go and read the information in a chronological order. So you're going to publish all the transactions to the bulletin board. And by the way, this is why privacy is going to be difficult with the systems, precisely because you need to know if a transaction has been made before. So all the transactions are broadcasted publicly. They're going to be ordered, they're going to be known. And so an optimization you can make on this bulletin board is also, you could reject invalid transactions. And now the system works if you allow invalid transactions. You could put all the transactions, valid, invalid, and then say, well, it's your job to look at the bulletin board and only care about the ones which are valid. But you can have the bulletin board reject invalid transactions. That way you look at it and you know that it's all valid. So that's essentially how you do eCash. The problem is, how do you actually create this bulletin board? That sounds difficult. And well, one way you could do it is by having a centralized mint. So you'll have a centralized company that mints the currency and that runs this website. The problem with that, obviously, is that you put a lot of trust in that mint. Well, they could reorder transactions, they could delete transactions, they could refuse transactions, they could go out of business. So that's difficult. You could use distributed consensus. So you could use state machine replication, have many mints, so many different actors who together maintain a coherent log. But already, that requires some tricky algorithms in distributed consensus to do this. It's not a trivial problem. But is there a decentralized solution where we're not relying on one mint or even a finite set of mints, but where anyone could really participate in the system? And so Bitcoin was the first protocol to propose a decentralized solution to this problem. And here's how it does it. So came out in 2008. So it's been 10 years now that, well, the paper came out in 2008. Bitcoin launched in early 2009. So it's going to be 10 years soon. It was the first successful cryptocurrencies. There were attempts before that didn't really work. And so in terms of design, so it uses proof of work. What is proof of work? Proof of work is a concept based on a partial hash collision. So a hash collision is when you take two different messages, you put them through a cryptographic hash function, and they give you the same hash. Now, if your cryptographic hash function is well designed, you're not going to be able to do this. It would be computationally infeasible to find a collision. However, you can ask for a partial hash collision. You could say, I would like 2 hashes to match in their first 10 bits, for example, or 15 bits. Or I would, if the hash of a message is a 256-bit number, I would like it to be below a certain value. And that way you can tune it, and you can tune the efforts that someone would need in order to produce such a hash. And that was introduced by cryptographer Adam Back in 1997 for email spam. So one proposed solution for email spam is to say, if everyone had to spend $1 or even a few cents to send an email, it's really bad for spam, because the way that spammers work is they send millions and millions of email, and then maybe 1 out of 10,000 will open the email and then will buy the product. If it costs just 1 cent or a few cents to send an email, most people will not mind, but it will be very, very expensive for spammers to do that. Now, the problem is you could try to tie email to the entire payment system and banking system, but that's very difficult to do. Like I said, it's a centralized system. It's not very programmable. It's fragmented. It's very, banking systems are different around the world. So you can't really do this with an open protocol like email. However, what you could do is you could say, you'll find a hash collision. It will cost you CPU. It will cost you time. It will cost you money. And we can force you this cost. Now, it's expensive because it's not a transfer. This money is not going to pay for anything. It's just going to be destroyed. But in some sense, it's a small amount of money. It can protect against spam. And for some reason, Hashcash didn't really take off. There are fields in SMTP to accept it, but it was not widely implemented by clients, unfortunately. And what it does that's really interesting is that it creates a tie between real-world resources, like computing power, electricity, and information. I was talking about how information is not scarce. You can always duplicate information, but this is scarce. This is something that you can verify mathematically, which is scarce. So that's interesting, and that's the first piece of building something like Bitcoin. So the second piece was the Nakamoto Consensus introduced in the Bitcoin paper. And so the way this works is that miners are so they're actors in the Bitcoin ecosystem. They produce blocks. What is a block? A block is a timestamp. So that's a time at which a miner claims a block was created. You have a commitment to a Merkle tree of transactions. So essentially, you take a lot of transactions, you put them into a hash tree structure, which is a cryptographic structure that commits you to the set of all transactions. You put the previous block hash. So a block is going to point to a previous block. And then you put a proof of work nonce. And the idea is that if you hash this entire header, it should be below a certain difficulty threshold. So you're going to fiddle with the nonce until your header passes a proof of work problem. And the idea is that you start with just one empty block, and then after that, people are going to compete. They're going to try to solve these proof of work systems and produce more blocks. So I find a block, I add it, I add it to the previous block, and so you have an entire ecosystem of miners who are going to expand this computing power and try to extend a chain of blocks and make it as long as possible. And if you do that, you actually have a consensus algorithm. But what's different is that whereas classical consensus algorithms are based on the principle that you have a set of n people, and then these n people need to agree, there's no set of people. The set of people is anyone with computing power. So anyone who has computing power can join into this algorithm. And then there's some drawbacks to that, which is also to say that, hey, if someone has computing power or more computing power than anyone else, then maybe they can have a disproportionate influence in the outcome. And the other idea of Bitcoin is that all these blocks and transactions, they're propagated on a gossip network in the same actually there's not a whole lot of gossip network that I can think about, but the idea is that you propagate your messages to peers and your peer propagates them to other peers. So it was based on the idea of using these peer-to-peer networks like Gnutella, for example, that were used for file sharing, but trying to have a peer-to-peer network for maintaining a ledger. So that was a breakthrough, and it has a few there's a few challenges with it. So one is you still have something called a 51% attack. So if I control more than 51% of computing power or hashing power in this network, then even though everyone who's honest is creating their chain, and I go out and I create my chain in my own corner, and my chain gets longer than the other one because I'm producing it at 51% the speed, and they're producing it at 49% the speed, so I go faster, and I keep my chain to myself, and then I reveal it, and then everything changes. So I can really, you can really harm the system if you have 51% of the system. The other issue is throughput. So Bitcoin produces 1 megabyte. They raised the size recently, but it produces this 1 megabyte size blocks every 10 minutes because it's based on a real network like the internet. You need to account for potentially long latencies and small bandwidths, and as a result, you can only achieve something like 4 transactions per second on Bitcoin, whereas networks like Visa are doing thousands and thousands of transactions per second. The other one is cost and energy expenditures. This is something that's really, really energy intensive. It started with CPUs. Today, people are using custom chips for doing this. And one of the major expense in producing these blocks is energy. And you have a bit of a Red Queen race between people because as more people put in more computing power, the difficulty of the proof of work challenges increases. And so today, I think you have a few $billion of electricity spent every year just to secure the Bitcoin network. Now, you have one argument, which is to say, hey, you know what, it's worth it. It's worth spending that money, but it raises the question of knowing if there's a way to do it more cheaply and without spending as much energy. There are other issues like selfish mining, which don't completely threaten Bitcoin, but which can cause some issues where some miners who have a large stake in the network without having 51% become more efficient than others. You have issues of synchronicity. So even though Bitcoin looks different than traditional consensus algorithm, it is actually somewhat more restricted in its assumptions. In the sense that this 51% attack, that works if everyone gets the blocks right away. If you can start delaying blocks in the network by 10 minutes, then it becomes a 33% attacks. And if you can start delaying blocks by hours, then it becomes something like more like a 10% attack or a 5% attack. So the safety of the system gets markedly worse if you can harm the network and the ability for blocks to be transited. But that's tied also to throughput. This is why you can't have a Bitcoin block every second, is because essentially of the synchronicity problem. And another one, which is more general, is protocol level innovation. So the Bitcoin protocol is a little set in stone. There's been a ton of research on the field of cryptocurrency since Bitcoin, and it's hard for Bitcoin to come to agreement or consensus over changes to its own protocol. So now I'm going to talk a little more about blockchains in general, take a step back from this Bitcoin design, and explain how blockchains work and where Tezos fits in. So statefulness in a stateless world. So the general idea for statefulness in a stateless world is that, I was explaining earlier that information can just be replicated. It's because all these equational systems are really, they don't carry any state. It's kind of like anything that you do in cryptography is kind of like doing functional programming in the sense that you don't really have states. You don't have mutation. You just have things, and then you could just copy them. Everything's immutable, and you can't change things. You can't say like I had money and now I don't have it anymore. And we would like to have this type of statefulness, but in the realm of cryptography, where normally we don't really have it. So, what is a blockchain? So it's a concurrent data structure. It's a data structure that many people can access at the same time. And it represents a shared, mutable singleton. So singleton because you only want one value of it. You don't want to have many possible blockchains at one time. You want to know which one is the right one. You want this value to be mutable. You want to be able to change the set of your ledger and the set of balances. And you want it to be shared. And the way you're going to represent that is as a linked list of blocks of operations. So like I said, like in Bitcoin, you're going to have a block, and the block is going to point towards a previous block. So motivation. So why do we do it like this? Because it's an append-only data structure. So it's an immutable data structure. What data structures are immutable? Simple values, simply linked list, trees, all of these are immutable data structure because you just keep adding to them. So you're not really changing the structure, you're creating a new structure that points to the old structure. That's what you do in OCaml all the time. Some structures are typically not append-only, like doubly linked lists, for example. Union find. Union find is this, like, it's one example that shows that there's some stuff that can be done in imperative programming that has a log n penalty in functional programming. It's the union find structure, or graphs. So how do we get mutability through immutable data structures? There's a simple trick. So let's say we had the word your, and we want to make a correction and call it your. Well, what we'll do is that we'll just point to it and say, okay, this is the old version, this is a new version. Voila, I've mutated it by just adding to it. And the problem is that as soon as you have concurrency, you have a problem because I edited it, but then you edited it, and then that person edited it. And so now we have two different versions, and that's a problem. If you have a simply linked list, in reality you have a tree, right? And the question is which leaf I'm going to take in that tree. Introducing the blockchains as essentially state monads. So the trick is that we're going to take a mutable state, and we're going to represent it through a series of operations. So for Bitcoin, your state is a set of unspent outputs. It's every balance that belongs to anyone that hasn't been spent, plus the total amount of work that's been done in a chain. We'll see why that matters, and the block number. And the operations that you have are going to be transactions. Okay, so generally speaking, in your blockchain, you're going to have a function called apply, which takes a state, takes an operation, and returns to you a new state. And we're just going to put all these operations into our linked list. Sounds great. And like I said, so in general, it can be a tree. So how do you pick a canonical leaf? So what you need is a well ordering over the branches. We ask for something a little stronger than that because it's easier to work with. We're going to ask a score function that takes a state and gives us a value of the state. So that way I have a state here, I have a state here, I have a state here. I'm just going to pick whatever state has the highest score and call that my canonical state. So essentially every blockchain implementation that you see can be subsumed by a pair, apply, and score. That's really every blockchain is built like this. And so how do you implement score? You have several options. So in Bitcoin, it's the total difficulty of the branch. It's the total hashing power for all the puzzles that have been solved in history. And so that's why I put the total work in the state, because I need to look at that, and I need to keep track of that to create my score function. You could be centralized. You could have a central party say, that's the right branch. They will sign the branch and say, that's the one. Or you could have something like proof of stake, where you validate, you count the number of signature that you can have in a certain branch, or the length of the branch. So different methods of implementing score. So in general, you can take a blockchain protocol and decompose it into 3 layers. One is going to be the network layer, which is how do you communicate with the rest of the world? How do you exchange operations? How do you exchange blocks? It's this famous gossip network. But it doesn't have to be a gossip network. You could have direct lines. You could have many different network architecture in order to communicate. You have the consensus layer, which is to say, okay, now we're getting all these messages. How do we agree on one consistent state? So that's the mechanism by which you're going to look at all of this information that comes on the network and decide what your state is. And the transaction layer, which is, okay, which we sometimes call the economic protocol. What do operations do? Like, what is the meaning of operations? And the way you get decentralization is by entangling 2 and 3, essentially. You're going to say, I'm going to use some stuff in my transaction layer to get consensus. So the way this works in Bitcoin is that, and I didn't mention, when you create a block, you get rewarded by newly created Bitcoins, so that you can transact at a later point. So you get some economic incentive for going to consensus. And that's the general idea of this blockchain protocol, is creating economic incentives for people to behave honestly inside the protocol. So now I'm going to talk a little bit about governance and self-amendments, which is a property of Tezos. So first, fork-based governance, which is what is most common outside of Tezos. So fork-based governance comes from the open source world. So traditionally in the open source world, when you have a project and you have a different view as to how the project should work, you fork it. So you had one version of the code, now you have two versions of the code, and you can have two different teams go in different directions. So for example, forks sometimes happen for licensing reasons. X386 and Xorg, for who remembers that fork, or OpenOffice and LibreOffice. But sometimes they just go because people have different ideas on where they want to take projects. And the nice thing is that as a user, I can choose. I can go with one version, and then a few months after, if I decide that the other people were right, I can switch to the other version. So this is great because everyone gets what they want. There's no scarcity. It's wonderful. But if you try to do that with cryptocurrencies, it gets a little trickier. So how does a fork work in a cryptocurrency? So let's say I had a Bitcoin, and now there's two different versions of the code base that run. Well, I'm going to end up having a Bitcoin in each of these versions. I'm going to have a Bitcoin version A and Bitcoin version B if there's two versions of the code. So at first, that's great. I have a choice. But do I keep both? Do I actually sell one of them to get the other one? Because if I have two, it's inconvenience. Like I said, I want to maximize optionality. I want to have the one that people are going to use. So I kind of have to make a decision. And then a few months later, if I made the wrong choice, then maybe one of them drops in value. And so now, I've lost money, and that's very inconvenient. It's not the same as changing your window manager. And so that's a limitation of fork-based governance. One of the versions in the fork is going to capture the value. And the question is, which one? So before I get to that, there's two kinds of forks, broadly speaking, that people talk about when they talk about cryptocurrencies. One is a hard fork. And in a hard fork, participants agree to change the rules of the protocol. We had a protocol, and we're going to have different rules. And the test for it is that blocks which in the past were invalid are now valid, right? So I have a different structure in my blocks. The old algorithm will look at this and say that block is not valid, but now we decide it's valid. In a soft fork, you only restrict the set of valid blocks. You change the code in a way that blocks that you would have accepted in the past, you now reject. And the nice thing about it is that if you're using an old client, you're not going to be, you don't need to update your own client. The only people that need to update are the people who produce blocks to make sure that they don't produce blocks which are now invalid. And there's this idea that a soft fork is somehow softer, than a hard fork, because you're not forcing anything on anyone. You're not telling people like, you need to accept invalid blocks, you need to upgrade your software. Oh no, you don't need to do anything. We're just going to narrow down the rules. In practice, however, with a soft fork, you can do almost anything that you would do with a hard fork. Almost anything you want. For example, here's an example of a soft fork. You could say, well, person number A can spend their, they used to be able to spend their tokens. Now we will only accept blocks where Alice sends all of her tokens to Bob. You could have a block like this. And so, you just restricted the set of what was possible, but essentially you've taken Alice's token and given them to Bob. That's what happened. And so, yeah, every hard fork you can almost implement as a soft fork at the cost of a little bit of complication. So which forks win? Once you have a fork, you have two branches, which one is going to win? So one popular theory with Bitcoin was that it was going to be the one with the most hashing power. The miners, they solve these problems, and they're going to choose one branch, that's the one they're going to care about, and that's the winning one. The problem is like, okay, but which branch do miners choose to put hashing power behind? Is it the one that users adopt? So if everyone prefers and values more one branch, then the miners would be crazy to spend a lot of resources on the other branch. They're going to want to go on the one that the users adopt. So maybe the users are in charge. Is this going to be the best one? I once read that Bitcoin didn't need governance because in Bitcoin we just take the best technological solution available and that's it. And of course that doesn't tell like who decides which one is the best one. That's a problem. You're just like pushing the buck. And I argue that the fork that wins is the one that is expected to win. Because of this money aspect, which is very circular, people are going to think, okay, what do people think the winner is going to be? And this is the one they're going to value. And so I should value the winner. It doesn't really matter if one is technology better than the other. Really what matters is what people are going to adopt. And that's completely circular. Everyone, in fact, could be thinking the same thing. Everyone could be thinking like, well, this version is worse than the other, but I'm going to pick this one because it's the most natural one and everyone's going to agree to that. So, you know, why does it matter that we agree? Why should we get along? Why not fork? Why not have many, many versions and everyone who disagrees gets his own fork? You know, competition is good. We'll have the best chain will win. We'll get a blockchain for everyone. And the problem is that the economics favor one chain. It's just more economical to have one token on one chain. And so what you'll have in doing so is you'll have costly destruction at first, where you'll have a lot of, you'll have potentially forking. And if something takes over the other one, you'll have value will be lost. And the other one is potentially stagnation. At some point, you get to the point where you can't really credibly fork. If you fork off the main branch that everyone is really tied to, then your fork has very low chance of succeeding, and therefore you have a very low chance of actually being able to innovate. In game theory, one example of that fork dynamic is called the battle of the sexes. So in this game, you have a wife and a husband, and here the husband would rather go to the theater, and the wife would rather go to the baseball match. So if they both go to the theater, the husband gets 3 points and the wife gets 2 points. If they both go to the baseball match, it's a baseball game, the wife gets 2 points and the husband gets 3 points. But they really care about being with each other, right? So if they go to different places, they're not going to be happy. And the weird thing with this game is that you have these two equilibrium, and each of them is going to try to convince the other one that, you know what, I'll go to the baseball game no matter what, I don't care. And it's very similar to the game of chicken, where you have two cars running at each other and saying, hey, I'm not going to steer. I tied my hand, I'm not even going to steer, so you have to steer, we're going to crash into each other. And you have the same dynamic when you see forks in cryptocurrencies, where no one really wants to fork, everyone wants to steer the direction of the main branch, and they'll say like, well, if you don't let me steer, I'm going to fork. And now we'll be divided. Now we'll be bad for everyone. So it's not a really good way to have. Governance. So again, on the branch that wins, one way of describing the branch that wins is the one that becomes a Schelling point. So that's it's a concept from Thomas Schelling, also called sometimes a focal point, and the general idea is that it's not the algorithm that controls the decentralized ledger, it's not the miners, it's not necessarily the developers or stakeholders, it's a social consensus. It's basically what everyone agrees is a ledger. So to give you an idea of a Schelling point, you need to meet someone in Paris, you both know the day, but you didn't set a time and place. Right, so where do you meet? And usually I have a pause here, so it's more dramatic. But the usual answer I get, it works almost every time, is you meet under the Eiffel Tower at noon. That's where you meet if you didn't set any details, because it's the obvious choice. Because Paris, the Eiffel Tower, it's kind of central, you'll find the person. Without coordination, it's what people would come up with. Train stations are also an acceptable answers in most cities. So that's a Schelling point. That's without coordination, you kind of agree on what's the natural one, and that's pretty much what dictates the result of forks in cryptocurrencies. So we try to do something different in Tezos, and we do that through the power of self-amendment. So the idea is that instead of changing by forking into a different version, we're going to try to change from the inside. So what I mean by changing from the inside is we're going to have changes to the code, but they're going to come from the blockchain itself. So how do we do that? Well, you remember the apply function and the fitness function? Well, we can treat those functions as a value and put them inside the state that we modify. So now the state of our blockchain, instead of just containing the state of balances or the total amount of work, it's also going to contain the function itself. And we'll have a new type of operation called an amendment, which can modify those. So now I can not just make transactions, I can also submit operations which modify the rules of the ledger. And in order to do interesting things, we're also going to let these amendments introspect into protocols. So the idea is that I can make changes to apply, but for my operation to be valid, I can require to have some structure on apply. I can say, I don't want to replace my apply function with just any function. The apply function that you give me has to have certain properties. So why would we do self-amendments? Because it gives us explicit governance. Now we have a very specific operation with very specific rules, like voting, for example, which would let us change the protocol. And that's kind of like having the rule of law. There's been a lot of contentious debates in Bitcoin around the block size or around the Ethereum hard forks. And the problem with this contentious debate is that if you don't have a hard rule to go by with, then it's kind of they kind of carry on forever. Reward innovation. Right now, today, if you have some cool idea in the blockchain space, everyone's tended to start their own blockchain because there's not a whole lot of reward for contributing to an existing one. But we can create an environment where if someone comes up with a new breakthrough, they can submit it to the Tezos protocol and then issue tokens to themselves as reward for having done so. You can solve collective action problems. So having a block reward in Bitcoin solves the collective action problem of getting security in the system. But there's others, like evangelizing, telling people about it, or maintaining and building infrastructure that's needed for the network. Let's say you want to build a mesh radio network for transmitting your blocks. That's something you can solve. And in general, you're creating coordination technology. It's not just money. Money is a tool of coordination, but blockchain is also a tool of coordination. What you do with this thing is, I talk about this super Nash equilibria. So in economics, you have the Pareto optimality. So the idea of Pareto optimality is that we have a solution to a problem, and I cannot make a better solution without making anyone worse off. So that's something that's pretty fair. I can't really improve it without hurting someone. And Nash equilibrium is no one benefits from deviating from that strategy. And the problem is that Nash equilibrium are not Pareto optimal, right? So the most famous example is the prisoner's dilemma, where the prisoners, they would both benefit from working with each other. So that's Pareto optimal. In general, cooperation is Pareto optimal. But their individual interest is to defect. So defection is a Nash equilibrium. And one cool theorem is that if you let people inside these games make contracts with each other, transact with each other, come up to agreement, then you obtain what is called a super Nash equilibrium, which is a Nash equilibrium that's stable against all contracts and coalitions. And every super Nash equilibrium is Pareto optimal. So the idea is that if you give people the tools to coordinate, then they're going to favor cooperation over defection. So it's a good way of getting people to work together. We're not getting the full super Nash equilibrium, but we're digging tunnels to Pareto optimality. All right, so that's just a very, very generic idea on blockchains and self-amendment. I'm going to speak a little more specifically about Tezos. All right. I'm trying to give a name to the consensus algorithm because everyone has a name. So I've been toying with the name Emmy, which is in the same vein as the name Mikkelsen. Liquid proof of stake consensus for Tezos. That's a lot of fancy words. So what is the general idea of the consensus algorithm in Tezos? So the idea is that we start from the Nakamoto Consensus. That's the one used in Bitcoin. And then we say, okay, we have this consensus, but it's very expensive. It consumes a lot of energy. And also it gives a lot of power to miners who are not necessarily the same people who use the network. So the first thing we're going to do is we're going to remove proof of work. And then we're going to have a whole lot of problems if we remove proof of work. And then we're going to fix all those problems one by one. And so that's the general design approach. What you end up with is an algorithm that proceeds in cycles. So a cycle is a set of blocks, and typically it's going to be 4,096 blocks who each belong to a given slot. Before a cycle, you determine a random seed, and we'll see how we do that. So picture yourself a cycle. You have 4,096 slots. In each of these slots, you're going to be able to fit exactly one block, and you have a random seed at your disposal. Okay, so to every slot, I'm going to attach a random priority list of block creators. So for slot number 1, I'm going to use my random seed and I'm going to say, okay, slot number 1 is yours. But if you don't do it, then after a certain time, you can do it. And then if you can't do it, after a certain time, you can do it. And these rights are granted randomly to anyone who holds any token. So if you own token in proportion to the number of tokens you hold, you can be randomly selected to create a block within a slot. That's a general idea. And we also impose that the slots are separated by at least a minute. Right? So a slot comes up, it's my turn. I create my block, I build on top of, I'm honest, I build on the top of the previous block. And then it's the next slot. And then after another minute, someone else comes in and creates another block until the end of the cycle. Another thing we do for robustness is that once I create my block, I want to prove to everyone that I created my block. It makes it easier because if they're malicious players, they could pretend that I didn't create my block. And so in order to minimize those effects, we're going to randomly also select 32 we're going to select 32 stakeholders. So you draw randomly across the set of all tokens 32 values and you look who owns them. And these people are going to get endorsement rights. So whenever I publish my block in my slots, there are people waiting to see this block, and they're going to say, oh, the block came, I'm signing the block, and they submit the signatures. So we have a block in every slot that's ideally randomized by 32 randomly assigned stakeholders. Okay, so that's pretty straightforward. How do we get a random seed? There's no randomness. We're running a deterministic protocol. So in proof of work, the randomness is external, in the sense that if you're just really hashing to solve a proof of work problem, you're really focused about the partial collision and not the rest. And so the rest gives you a lot of randomness that you can't really optimize for. Here what we do is we use a commit reveal scheme to generate entropy. So you have different people commit to a random number and then reveal it at a later time, and you use the different revealed random numbers to get some entropy together. And there's some subtleties around that, but that's a general idea. So you refresh your entropy, you have a cycle, you assign the rights, and then you keep going. And the score of the chain is going to be essentially the total number of endorsements that you have on this chain. And another optimization yet is that if you're a block producer, if you're an endorser, you will have to put safety deposits to prevent equivocation. Equivocation is when someone creates 2 blocks at the same height, because you want people to commit to one version. So before I create a block, I'll have to put up a deposit. I'll produce my block, and if anyone sees that I created another block at the same height, they can go and denounce me on the main chain and say, hey, that person created 2 blocks. They were only supposed to create 1. And I lose my safety deposits. The safety deposits, beyond the risk of equivocation, they also ensure that anyone who is actually producing block and participating in the system is actually holding tokens and has, in some sense, a network's best interest at heart. So that's general explanation of the algorithm. It's something that was designed in around 2014, so proof of stake was very new. There's been a lot of research in proof of stake over the past, I would say, essentially 2-3 years. And a lot of interesting results have come. You'll see there's a lot of impossibility results above proof of stake. But the devil is in the details. You have impossibility research for certain properties, but oftentimes the properties that you care about are slightly weaker version of the properties that you cannot obtain with proof of stake. So pros and cons of this algorithm. So it converges very quickly to consensus when the endorsers are reactive. Like the fact of having 32 endorsers that you sample randomly in a network, after a few blocks, after a few times that you've selected 32 random person, you've selected a large fraction of the ownership base. And if they all agree on his history and they're honest, they're unlikely to depart. So your blockchain is going to converge pretty quickly. It has good liveness in the sense of your blockchain is always going to keep making progress. If they're not reactive, you're still going to be able to get transactions through. You're still going to be able to get blocked. You're still going to be able to make progress. And also, it has fair block creation rights. It really insists on this. It's the idea in Tezos that if you own 1% of the tokens, you should be able to create 1% of the blocks. And that's something that's missing from a lot other proof of stake system, and Tezos works a lot to try to achieve that. Some of the cons of this algorithm, there's no finality. So like in Bitcoin, you don't really know if a transaction has been included forever in your ledger. You could have someone, in theory, come up with a longer chain or a better chain. And so statistically, it becomes very, very unlikely as time goes by that your chain will change, but you don't really know. You don't really know for sure. And the other one is just like Bitcoin. We also have here a synchronicity assumption, and that's the reason why why wait a minute? Why not a second? Which is that you need an honest majority for the system to work. But if people can start delaying blocks and messages by more than a minute, then all of a sudden your honest majority needs to become larger and larger, right? If you can delay message, like trivially, for example, if I can delay every message by 2 minutes, right? I can create my, and I have 25% of the network. I create, so I don't know, if I have 33% of the network, I'm going to create blocks at 1/3 the speed of the other guys. But then if I can slow the other guys who are doing at 2/3 the speed by a factor half, because now they need 2 minutes to propagate their blocks, then they're going to go the same speed as I do. So if I can delay stuff by 2 minutes, now I need to have 66% honest majority. So that's not really great because you're baking in this assumption, and it prevents you from going faster, but you have some benefits in terms of liveness. Smart contracts in Tezos. So Tezos is a smart contract platform. I haven't really mentioned that yet, but beyond making money on these platforms, you can also create contracts where you're going to program that money and programmatically agree on how it can be used. But you can also do more things. So people have used smart contracts to build games, to build domain name systems, to build all sorts of things. So the usual approach when you create a smart contract language, and when I say usual, I mean those 3 or 4 approaches which have not been Tezos, have been that you create a virtual machine, and then you have some high-level language that people program their contracts in, and you'll compile down to the VM. And the benefits of doing this is you can count the cost of operation very easily because you just count the steps in your virtual machine, and it's very generic. You can have all the languages you want. You'll just compile down to that simple and minimal VM. And the downside of this is that if you want to really understand what you're doing, well, you need, first of all, a formal specification of the VM. That's not so hard to get. But you also need a formal specification of the high-level language, and then you need a formally verified compiler to make sure that when you write a contract, you're going to get what you expect. And the reason for that is these contracts can hold hundreds of millions of dollars, and so the cost of bugs for these contracts is very, very high. And it's not just if you have a bug, you don't just fix your compiler and do a new build. You can't really change the smart contracts when they're deployed. So cost of errors is enormous. And so what do we care about for smart contracts? Well, we care about correctness enormously. Like we don't want our smart contract to have any issue. We care about verifiability. I also care about being able to prove everyone that my smart contract doesn't have any issue. It's not enough for me to be confident. Everyone needs to be confident. We care about parsimony. So space is expensive on a blockchain. It's at a premium. Everyone needs to keep everything that's on a blockchain on their disk or even in memory if you want to be efficient. So we don't want to have heavy programs. Performance, not really an issue because we're not running ray tracing here. We're running simple logic. Portability, not really an issue. You're just, you're mainly running on your own blockchain. You're not going to be running it on like a dozen different platforms. So yeah, it's business logic, not protein folding. So the design goals for the language in Tezos was that it should be generic. Like you want to be able to do anything. So you don't want to just start with like a domain-specific language for contracts or finance or anything like that, because you can use smart contracts for many different things, and you don't want to take too strong of a view of what it's going to be used for. You want something that's safe, and that means at least type safe. You want something that's readable, because people will look at the contract and try to understand what it's doing. And you want easy gas accounting. So you want to have a chance of to count the resources that the execution of a contract is using. So there's a tension here, because if you want something generic with easy gas accounting, well, you want this assembly-like language, you want this VM approach. But if you want safe and readable, you want something like a high-level functional language. And so Michelson, which is a language for Tezos, is a compromise. It's a low-level language, but it has high-level primitives. It's stack-based for easier gas calculation, so it doesn't have any variables. But you have annotations, which are pretty helpful. It's statically typed, it's functional, and it's a little bit Lisp-y. So this is Michelson on a postcard. This is everything you have in Michelson. So we have some nice data types, like natural number. So a natural number, that's a positive integer, no bound. So you're not going to have any overflow bugs in Michelson. We have an integer, so an integer could be negative. Again, by default, no bound. Timestamps, signatures, hashes, contract, amounts, all of these are typed separately. And then you can build more complex type by using either left-right to create sum types or pairs. And we also have a sum and none. So you have all of these nice types. You can also create structures like maps. You can also create lambdas. So this is a fairly high-level language. At the same time, you will see something that's more like assembly-like, at least for a stack machine, like drop, dupe, swap, push, all of this type of operations. And then you'll have the do I even have them here? Yeah, you'll have the weird loops that we have on the chain. I think that the instruction data has changed slightly since I did this slide. So it's basically a fairly small language, but you can do a lot with it. Here's an example. So there'll be presentations going more into Michelson, but I'm just giving you a quick overview. Oh, that's an old example. We don't return anything anymore. I need to update my slides. So in this example, you have a map which maps strings to natural integers, and you return you don't return anything anymore. And you have a parameter which is a string. So here, you grab the amount that was sent to the contract, and then you give it a little tag. You push the amount 5, because what was required to play with this contract is to push at least 5. You compare, and if 5 is greater than what was sent, then you fail. That's not good. And otherwise, you do a lot of stack manipulation in order to get your storage. You grab you grab this string from your map, and if it's not there, you fail. Otherwise, you're going to push the integer 1. You're going to add it, and then you update your map. And so basically, what you can do with this thing is people can pay 5, and they can vote on island, not island, or boat. That was a slide for a financial crypto conference where they wanted to vote on whether or not it was okay to do it on not an island, which is a tradition, or on a boat. So anyway, that's a very simple example of Michelson. So it mixes fairly understandable and readable parts with annoying stack manipulation, as you'll see. But once you use an IDE, it gets a lot easier to work with. Okay. So that's a brief presentation of Tezos. Let me speak a little bit about the road ahead and stuff which are coming in Tezos. So first of all is security. So Tezos has been in development for a while. It's been live for a few months. But if you don't have security, you don't have anything here. And so improving what we have, improving the security of what we have is paramount. So that can mean just like keep writing more tests, keep doing more checks. There's also things that we know could be improved, and we know how to improve them, but they just need to be improved. But if we're looking just like beyond that, just like formal verification of the code. So part of our codes are already formally verified. The libraries we use for cryptography, some of them come from Hacklestar, which is a project for F-star implementation of primitives. We also rely heavily on the OCaml type system to make proofs. So for example, the Michelson, the way the Michelson programs are composed, they are well typed, and that's ensured by the OCaml JDT. So if the OCaml JDT implementation is correct, then we know that any Michelson program that you can get in the protocol is going to be well typed. So there's some uses of the type system, but beyond that, being able to formally verify some of the modules of the code. So either formally verifying directly the code, or even taking things like the consensus algorithm, modeling it, and having formal proofs about the model of the consensus algorithm, all of these things would be very helpful. Upgrade the consensus algorithm. Like I said, the consensus we have is from 2014. I think it's pretty cool. And as far as chain-based proof of stake goes, it's pretty state of the art. You'll probably hear about Cardano and Ouroboros, so they have a lot of published paper and peer-reviewed papers around Ouroboros. The proof of safety that they have for their algorithm pretty much apply to Money and Tezos, but we have a lot more protections against selfish block creation and a lot of more protections for fairness, faster conversions. So we have nice properties. I think it's competitive with what's out there, but it's important to look ahead and get something that's really, really state of the art and well proven. So that's for the security aspects. Privacy, I mentioned how important privacy is, and right now Tezos doesn't do anything for privacy. So the first thing would be to have private transactions, and there are techniques that can be used from other projects like Zero Cash, for example. Zero Cash is a paper, Zcash is a project. So Zcash has really nice private transactions using zero knowledge proofs. So importing these techniques. But going beyond that, private votes. Right now, all the votes in Tezos are public. I think we'd benefit to have more private votes, and there's cryptographic primitives that can be used to do that. So the homomorphic encryption is typically difficult in cryptography, but for votes, you're only adding stuff. So if you're just adding and not multiplying, you have a somewhat easier scheme. And going even beyond that, private smart contracts, where it's not just a transaction, but like any smart contract that you want, be able to just put it on a blockchain, and then the blockchain just verifies that the contract is correct, but doesn't have to have knowledge of the contract itself. Scaling. So paradoxically, at the same time, there's a little adoption of cryptocurrencies. It's still niche, but the people who do adopt it have been needing more throughput, more transactions per second. It's been hitting capacity on Bitcoin, it's been hitting capacity on Ethereum. So increasing the throughput is something that can be done simply with the existing algorithm, simply by cleaning up some stuff, making the the nodes more efficient. We can just put more transactions on it, having smaller representations for transactions. So there's a lot of very low-hanging fruit here for throughput. More fancy stuff we can scale with non-interactive zero-knowledge proofs of knowledge. So the general idea is that instead of putting transactions in blocks, you now just put a single proof that there are transactions that exist, which have a certain effect. You don't need to have a very large witness for all the transaction. You can have a constant size witness using zero-knowledge proofs. So you can cram a lot of transaction into a few bytes. So that's very, very powerful, but still largely inefficient because these proofs are expensive to create. Sharding. Sharding is a technique where instead of just having one blockchain, you have many blockchains that go their different ways and get reconciled once in a while without the need for everyone to validate every blockchain. So there's a lot of technical difficulties with that. I'm more interested in these two scaling approaches, but some of that is being researched for Tezos at Cornell, and I think there are really good proposals coming for sharding. So different approaches. And no, I don't have a conclusion slide. So that's basically some of the road ahead for Tezos. And my general presentation, like I said, I want to leave time for questions at the end because I probably covered stuff that all of you already knew, and I probably went too fast on stuff that you don't necessarily know. So please, if you have any question, let me know. Or rather, I've learned recently, you don't ask, do you have any question? You ask, what are your questions? Or I'll start naming volunteers. All right, Diego, why don't you start?
So my question is, in the roadmap, we have to upgrade the consensus algorithm. And what are the elements that you think that in the current consensus algorithm are weak and that should be considered a priority?
Well, I've changed my mind over it. The what? Oh, yes, yes. So the question is, I mentioned changes to the consensus algorithm. What parts of the consensus algorithm do you think are weak and need replacement? So there are several things. I think that it's a weakness that we don't so let me rephrase it. The consensus algorithm in Tezos takes a belt and suspender approach by using a lot of different tricks from different papers in order to just pile on safety. We'll create blocks in a certain way. If you could have proof set of correctness of the algorithms without using endorsements, just by adding blocks one after the other, and you could get safety arguments from that. But we add endorsements because heuristically it will give you faster conversions, and heuristically it will give you less selfish mining. Likewise, we use a system of tracking roles in order to make sure that we don't randomly assign the rights to just certain accounts, but we track the ownership of the token so that if someone tries to do a chain on the side, like a secret fork, they can only do it using the tokens they own and not look like they have a wider variety of token to use for. So there's a lot of heuristic tricks that are used. And the problem is that we like a good formal specification of the algorithm. And it's a problem not so much because I think it's not so much about the safety of it, which I think there's really strong arguments for. It's more that you can't really tweak it if you don't have a model you can run it through, if you don't know what the limits are. So for example, I think it would be interesting that the endorsements for a block could be included not just in the next block, but in the 3 following blocks. So that if the next block refuses to include endorsements in order to make the chain weaker than it should be, then they could be included in the next few blocks. So if I think about that, heuristically it seems like a good idea, but at the end of the day you don't really know until you have a model where you can actually try this out. Now, it doesn't actually have to be a mathematical model. It can be really good simulation, as long as you have really realistic attackers in the simulation. But of course the gold standard is a mathematical model. So having really good mathematical model of these things makes it easier to really understand what your limits are, how fast. So you have a synchronicity assumption in Tezos, but how exactly does the chain react to delays in the network? Maybe it's something you can observe in the rate of endorsements, and so maybe it's less of a problem. Knowing this exactly, you get it from simulation, you get it from modeling. So we don't have that, and that's I think is an issue. Going beyond that, so the synchronicity is annoying because you always have to make assumptions about the state of the network, and they are a synchronous protocol out there. There are weakly synchronous protocol and there are asynchronous protocol. And the nice thing about this is that you can go really fast, because if you can't make assumptions about the network, you have to be conservative. You have to say, I'm going to wait a long time before I consider that this person did not produce their blocks. If on the other hand, you're not dependent on these assumptions, then you can be very optimistic. You can try to go really fast as you want. And then if somehow if somehow the network has delays, then you have delay. So you want the delays in your chain not to be worst case, but to actually reflect the state of the network. And improving upon that is very helpful. So the weakly synchronous algorithm and asynchronous algorithms that exist, they are typically algorithms that also provide finality. So on a given block, you'll know that the block has been accepted by the honest majority of the bakers, and that's essentially why you get this property of not depending on network delays, is because, well, if there's network delays, you might not get your block for a while, but once you get it, you know that's it. You know that it's not because you haven't received another message, because that's the only message that you could potentially receive. So these are interesting. These don't scale as well to very large number of users. There's interesting proposals of using sortition, for example, to use subsets of large subsets of validators in order to create blocks. So to go back to your question, I think lack of a good formal specification and model that we can use to tweak and understand better. And the second one is, but that's for just old chain-based algorithm, the timing assumptions. Jérôme?
No.
Right. No one has any question? Everyone understood everything? All right.
So,
Nicolas is in first. Benjamin, you next.
About the privacy on Tezos.
Yeah.
I didn't know it was planned for Tezos. I don't know if the market wants that. Is it planned on the roadmap to develop the privacy on Tezos?
Is it what?
Is it planned to develop the privacy on Tezos?
On whose roadmap? So this is what I think is important. So yeah, sorry. Nicolas' question is it planned on the roadmap to develop privacy on Tezos? And so my answer is whose roadmap? So this is my presentation. This is what I think is important. You guys are going to want, you guys are going to work on what you're working on. I suggest that. I think it's important. I think it's cool. I think it's going to make a difference. Right now, there's this type of segmentation that people do in this market, where they say like, well, some projects, they're platforms, they're smart contract platforms, and some of them are currency, and some of them are private currencies, and they look at them as if they were distinct categories, even though there's nothing that prevents anyone from just like being in all of these categories at the same time. So I think it's a very important, privacy is a very important property to have, and it has benefit beyond privacy, like scalability. It has benefits in scalability. It has benefits in fungibility, so that all the tokens are the same. If you can have anonymity, then all the tokens are essentially the same, because you can't just like track them and say like, oh, it's this one versus this one. It also has benefits in censorship resistance, because if you can have anonymous transactions, then you can't just say like, I'm going to refuse your transactions because I don't like you. So to me, it's very important.
Can you say a little bit more about open law? So I saw that there's a grant given to, I forgot what research.
Open law?
Yeah.
Not familiar with that. So the Tezos Foundation gives out grants. I remember they mentioned the grants to Close, which does legal smart contracts.
Yeah, with Accordion project.
The what?
Accordion project
Accordion?
and Ergo.
Clause, yeah. I don't know, so...
I mean, if it's just like to go from Michelson to their language, or?
No, they're building a compiler from their language to Michelson. So one thing I didn't mention about Michelson is it's also a pretty good compilation target. But I don't know the details of the Close project.
And how about the regulations? I saw that France is one of the pioneers looking how to, what's the status of blockchains? Like, for instance, with GDPR and like they say that they have a problem, basically, like the right to be forgotten if you have
right. So the question is about GDPR regulation and how that interact with blockchain and the right to be forgotten and so on and so forth. I don't think anyone really knows at this point. I don't think the regulators know, and the lawyers aren't sure, and the people building blockchains aren't sure. I mean, so far it doesn't. I think it's mostly going to be incumbent on the platform developers. Like if I build a smart contract and people put their information in a smart contract, as a developer of the smart contract, it's my responsibility to make sure that I can comply with these things. I don't. But the idea on the blockchain is not really to put some. The idea on the blockchain is not really to put some personal information. Like I don't. There's some. You sometimes hear these speeches about, oh, we'll put your personal information on a blockchain, that way you own it. Like, how do you own it? You just made it public. So that doesn't make a whole lot of sense. I know that, I read that GDPR was okay with deleting private keys as a way of deleting data. So if you had a private key for something that was encrypted and you delete the private keys, that's like deleting the data. So there are solutions around it. But for most of the use cases, which I think are going to be on a blockchain, I don't think is going to be that impacted by GDPR. I also don't think that GDPR applies to the case of like, I wrote a check to this merchant and I want this merchant to forget that I wrote a check.
I guess you should try to have some contact with people working on this. Like, okay, what would be the status such that you share your point of view with them, such that they, since they have difficulties classifying it, or what should it be? Maybe they should interact more with blockchain developers such that they're...
Yeah, that would be great. Well, if there's any regulator who's interested in discussing the interaction of GDPR and blockchain technology, I'm happy to explain what the blockchain technology is like on the blockchain side. But
so who is watching us remotely from I don't know where, but in Vietnam, had two questions. One of her question was pretty similar, which was, will normal people be able to write legal smart contracts in the future? And I think the close project will probably give us a little bit of answer. I hope so. The second one, I think, is a good introductory question, because I think a lot of us here in this room ask what, so we understood technically what this object is, but what do we do with it? And one question was about, we hear a lot about running a healthcare system on top of a blockchain.
Yeah.
How would you do that?
Okay, so three questions. First one is, will normal people be able to write these legal smart contracts? The second one is, what are some of these use cases? And the third one is, you hear a lot about putting healthcare on the blockchain. What is that going to look like? So for the first one, actually the people behind Close have a partnership recently with LegalZoom. LegalZoom is this website where you can do things like, I think you can do things like a will, or like starting a company, or all that. And the particularities of the type of contracts that they do is that they're very, very standard and cookie cutter, right? If you write a rental agreement with someone, you really only have to put in a few parameters to your rental agreements and decide if you want this term or that term or that term. It's like, I've been to these websites for lease agreements, and it's like, okay, should the tenants pay for replacing keys, and then how much, how many days for late payments, and so on and so forth. And I think we'll see a lot of that. I don't think people are going to be writing directly, like just anyone is just going to be writing contracts in the same way that I wouldn't write my own lease. But I think you'll have templates and parameters that people can use. In terms of applications on the blockchain, so more than the big dApps, which are popular in Ethereum, where it's like, let's run an entire program on the blockchain, I think simple, small financial contracts are going to be valuable, like small insurance contracts. I had an issue with a car I rented back in January. And I bought the insurance when I rented the car, and I called them and they said they would pay, and I've been trying to get them to pay by email for more than 6 months. And so if at the very least it had been in a smart contract where they would have to commit, because they don't want to tell me that they're not going to pay, but they also like just keep delaying and delaying and delaying. So if this thing was in a smart contract, it would force them to actually go ahead and acknowledge that something is owed. So like tying, like bringing some visibility in claim processing, I think would be helpful. Also, smaller ticket items, ensuring something for a value of like $100 or even $10. That's not something you can really do nowadays. So for me, that's an interesting application. Other ones which are not necessarily financial, domain name systems, for example. Right now, DNS is controlled only by a few entities. It's not very secure, and having a better system for names and strikes me as a better approach. It's an interesting approach to PKI, So the web of trust systems for keys hasn't really worked very well, but a system on a blockchain where you can actually have an identity and then attach keys to it might be a better fit. So the question regarding healthcare, are healthcare records going to be put on a blockchain? I just don't see it. People talk a lot about it. I don't know too much about the healthcare markets. Obviously, they would not put your actual healthcare record. So what? They're going to put like a hash of your healthcare record on a blockchain, and then so what? There's a tendency in some industries to use a blockchain as a stone soup. So the story of the stone soup is that someone comes into a village with a pot and a stone, and they go in the center of the village, and at first they go to the villagers and they ask for food, and no one wants to give them food. So they set up a small fire, they put their pots with water, and they start boiling the stone. And the villagers are very curious, and they go to the person and they say, well, what are you doing? And they say, oh, I'm doing stone soup, it's delicious, it's going to be great. And they're like, are you sure? Oh, yeah, but like stone soup is delicious. It's even better with a little bit of carrots. And so the villager says, like, well, I'll spare a carrot. Here's a carrot. And then someone else comes by and they bring a potato, and then they bring some meat, and they bring some salt and all of that. And at the end, they drink the soup, and they're like, it's delicious. And the guy says, yes. And not only that, you can reuse the stone. So there's a lot of fragmentation in a lot of markets, financial markets, probably the healthcare market as well. They need an overhaul of their IT solutions. And I think sometimes some vendors are coming in with what essentially are like reasonable solution and just calling it blockchain to get the middle managers or CEOs to sign off on it and get it adopted. A recent example is, I think it's Walmart said, they deployed this Hyperledger blockchain. It's an IBM solution. And they said, all right, now everyone who sells us lettuce has to put everything on the blockchain. And some people are saying like, oh my goodness, that's like, oh, now with blockchain they can track the provenance of lettuce in 3 seconds. Yeah, but like the way this works is because Walmart is compelling all of these vendors to input their data into a single system. The blockchain doesn't actually do anything for it. But maybe they were better able to convince the lettuce producers by saying like, oh, it's blockchain. So there's some of that going on, definitely. And I think that maybe what's going on with healthcare. But I could be too cynical. Anything else?
Yes.
Oh, wow. All right, you first, and then Chris.
Do people write their contracts in Michelson directly, or do they prefer high-level alternative like liquidity?
Oh, they all prefer high-level alternatives. So liquidity was a language developed by OCaml Pro that compiles down to Michelson. It's pretty much a subset of OCaml. So people have been using liquidity. Michelson is not, I think there's only a few people in the world who have written Michelson contracts. I grew to like it. And the thing is like, you're going to write a contract, right? You're going to spend so much time verifying it, understanding what it does, and it's going to be a few lines. The overhead of writing it in Michelson, I don't think is very large. And if you look, there's, for example, we have an example of an atomic swap. An atomic swap is when you exchange some tokens from one blockchain to another. So there's an example in Michelson that's fairly compact of an atomic swap, and you look at it and it's fairly readable. And then there's one which was done in liquidity, which is popular, which is about like 10 times the size once compiled. So, I mean, compilers can be improved, but there's something to be said about writing in Michelson. I think most people will not end up writing in Michelson. I think they will end up writing in high-level languages when they develop their applications. But then there will be some very, very specialized application that will do direct to Michelson. Like, let's say you're writing a wallet, for example, and you want some multi-sig ones. You just spend, you'll invest the time and effort to really get it in Michelson and really, really optimized. Because you can actually do that. You can hand optimize Michelson. You cannot hand optimize EVM code for Ethereum. So some highly used, highly deployed contract will be like this. And then when someone just says like, oh, try out my new dApp, they will probably not use Michelson for that.
So do we have proof of compilation from liquidity to Michelson?
Nope, no. Okay. So building a certified compiler would be helpful, but also, more than, so liquidity is XML, which is nicer than doing Michelson, but I think a lot of people would like something like a simple, statically typed, kind of imperative language would be very helpful for most people. Something like a Python or a Pascal.
So my question was more market-oriented perspective, I would say, about things I heard at the OECD, and I wanted to take on this. What do you think about the combinations between permissionless and permission blockchains, and also private versus public blockchains? This was discussed a lot.
Right, so the question is about permissionless versus permission blockchain, private versus public blockchain. So there's some there's some dispute about what people mean by permissionless. So for me, if there's not a set of like people who are the one who control a blockchain and anyone can really join and participate, for me that's permissionless. They are very strong Bitcoin proponents that will tell you that if you're not using proof of work, it's not permissionless, because in proof of work, anyone can come in with a CPU and create blocks. Not really true. You need to buy, like you're never going to create a block unless you really buy like specialized equipment from a few vendors. Whereas in proof of stake, you need to buy tokens. And so what if no one ever buys your token, then you can't participate? Not really realistic, but so that's sometimes when people talk about permissionless and permission, they talk about the consensus. For me, it's more about like, are you allowed to deploy a smart contract? If anyone's allowed to just go out and deploy smart contracts and use it as they want, that's what it means to be permissionless. On the contrary, permission or private blockchains are going to be used by a small consortium of people, and they don't let, they're not going to let anyone else in. It's a finite number of people. So several questions about permission blockchain. Are they useful? So a lot of permission blockchain, there are situations like the Walmart type of situation where it doesn't really do anything. There are situations though when I do think that there's a place for permission blockchain in some context, mostly consortiums. So if you have a consortium of enterprises that don't really trust each other, and also you have a political problem, you could maybe solve it with having a database run, but not, but every one of them is going to want to run a database and run it their way. And one way to cut the Gordon knot is to say, okay, no one has it. We're going to run a replicated ledger, okay? So that's one way of solving the problem, and you get nicer properties with a blockchain that you don't get immediately with a database, like the auditability of it, the cryptographic auditability of it. So there are some benefits. So I do believe there are real benefits. When you are in a situation where you get real benefits from a permission blockchain, I don't think it makes a whole lot of sense to use a permissionless blockchain. Like, you're going to be better off. It really depends on your threat models. But if you are a bunch of letters producers trying to produce letters, and you form a consortium and you use this blockchain, the type of scenarios that you get protected against in public blockchains is so different than what can match. I mean, if you have one letters producers that starts misbehaving, and you know who they are, and you go to them and you say like, hey, you're creating a bunch of blocks that we don't like, we're kicking you out of a consortium, and that's bad. So you have all these human institutions that can come in and help you out. So there's not really a big benefit. I think the benefits of using a public blockchain is when you want to be truly global, so that you want to be available everywhere, very widely. It's not just a consortium of a dozen people, but potentially thousands and thousands of people across many different jurisdictions and countries interacting with each other. That's where it makes sense to have public blockchains.
But that also makes it more challenging to have smart contracts, that work globally.
Yeah. Oh, so
They make more sense to have for private ones, like, okay, the permission one, financial applications or whatever, and you have permission ledgers, and then it makes much more sense to have smart contracts than everybody deploys the same.
So you're saying that it makes a lot more sense to have smart contracts on private ledgers than on a public ledger? I don't think I agree. I mean, it depends what you're trying to do. Again, if you're trying to interact with many different people across many different jurisdictions in a permissionless setting, you do want smart contracts. They're very useful, and you're not gonna, and you still need to have those. So they're useful in the private settings. They're useful in the public setting as well.
Yeah, but that means that every node I think we'll deploy that contract, and maybe
yeah, right. So what you're saying is every node participating has to deploy the contract. So that goes back to the idea of sharding, where essentially you're saying, okay, maybe not everyone needs to run everything and validate everything, because that doesn't scale very well. And the idea is that say, well, let's say maybe we'll have 10 blockchains, and then the contracts can live on different blockchains, and then you can validate on a single one, and you have economic incentives for the validators of different blockchains to synchronize once in a while and make sure and kind of trust the work of the other one. And that could come in different forms. One blockchain could exchange with the other one a zero-knowledge proof that it's done its job correctly, and then now you don't have to validate it because they validated it for you. So that's one solution. Another solution would be economic incentives. So you have different ways of having shared security between a lot of different blockchains. Another approach also is layer 2 solutions. So you don't really build on the blockchain directly. So you and I want to enter a contract. Instead of just doing everything on a blockchain, we enter the contract privately. And but we tell the blockchain about the contract. Maybe we put a hash of the contract on the blockchain. And only if we have a dispute over the contract do we take the dispute to the blockchain. So we do our transactions, and then you refuse to.
They're called off-chain?
Off-chain, yeah. So we do an off-chain contract together, and you're supposed to pay me some money. You don't pay it to me, and so we keep track of all our interactions. We run a mini kind of blockchains between the two of us. It's just transactions signed back and forth. And if you cheat, I go to the blockchain and I say, well, we had a contract. We told you about this hash. Well, here's the contract. Here's the content of the contract, and here's the content of our transaction. And look, she cheated, and you had to put a performance bond at the beginning. And then I get paid out of the performance bond. So there are ways to do off-chain contracts like this without.
They're trying with Casper?
So Casper is Ethereum's approach to proof of stake, and it's been referring to about half a dozen different designs. So the latest design for Casper, if I understand, is that they have some underlying blockchain which runs somewhere. Maybe it's a light proof of work, maybe something. So they run a fast blockchain, and then once every 100 block or something like this, they get to a Byzantine agreement over a branch of the chain that's the main ID. And then they're also doing sharding, and they're trying to do sharding at the same time as Casper, and so now they call it Shasper. And again, they've tried to do different approaches for sharding. So that's one of the things they're doing. But that's sharding. For off-chain contracts, one of the things that Ethereum has been proposing has been Plasma. But Plasma doesn't really work for smart contracts. It kind of works only for some stuff like decentralized exchanges or like just having another token. So there's not a whole lot of, I would say the closest thing to a completely off-chain smart contract would be something like Truebit, which was proposed for Ethereum. So there's different approaches. A lot of people are talking about that. I don't think we're there yet. There's low-hanging fruits for throughputs that haven't really been picked before we get to this type of optimization.
When I had talked with Diego a while back, he put what we just talked about in a nice way, saying that basically you have to view the blockchain as a distributed courtroom where you only involve other people if you have a problem on a contract. What you were saying, that basically you fire the existence of the contract, and you see it as a sort of courtroom where everything is deterministic, so if you lose, you're going to lose.
Yeah, so what you're saying is that you can use the blockchain just as a courtroom where you just adjudicate contracts. You don't really run your transactions or your contracts. You just do whatever you want on the side, and then you just go back if there's a problem. So that that's definitely an interesting vision, and I think there's a lot of truth to it for contracts. The downside is that you need to put up performance bonds, and so you have to lock capital that might not otherwise be locked. So that's part of the potential downsides. I think that's part of the vision, but I don't think it has to be just radically just that. I think you can have some activity on the blockchain itself and do different things.
One question that came up a couple of times during my visit in Italy is why Michelson is Turing complete. For them, Turing complete is so 80s. It's something old, and so I mean there was something that I couldn't really explain why the design choice was taken at the beginning. like your data can evolve in something more less.
Absolutely. So the question is like, why is Michelson Turing complete? That's so 80s. And here's my answer. So I have a blog post where I talk about that, actually called Turing Completeness Was Framed, where I talk about this. And there's also a very good presentation at PBase 16, I think, of Andrew Miller on Ethereum is not Turing complete and it doesn't matter anyway. So I recommend those. I recommend those two things. But I'll recap the argument very quickly. The first thing is that Michelson is not Turing complete because you have to pay gas for your operations and you have a finite amount of gas. So it is bound in time. And so because it's bound in time, it's not Turing complete. Now, what is the problem with Turing completeness? The problem with Turing completeness is Rice theorem is that you cannot have a general algorithm that will prove that will be able to check non-trivial properties of any program, like termination, for example. The problem is that some people believe that the converse of Rice theorem is true. What they believe essentially is that if you're Turing complete, then you cannot prove anything about any specific program. And of course, that's not true. The vast majority of programs which have ever been written can be proven. Many properties can be proven about them because programmers mostly care about writing contracts, writing programs that they can prove work. You know, even if you're not doing a formal proof, you have some proof in your head that this thing is going to do something. So what happens if you write a program that doesn't work, where your proof is wrong? Okay, then you've written a bad contract. Okay, so you shouldn't be writing bad contracts. That makes sense. But then you're only really hurting yourself and the people hurting your contracts. So at the system level, it might be bad reputation if you have bad contracts, but you're not really hurting the blockchains. You'll be cut after a certain amount of gas execution step, and that's it. You know, that's your problem. If you write contracts where you can prove a whole lot of properties, that's great. If you want to prove termination of your contracts and then show everyone, hey, my contract terminates, that's great. You can do that. So really what matters is not so much how, is this Turing complete, but how easy to prove properties above this contract, right? And so one property you might want to care about is, hey, maybe I don't care about termination, but I care about termination in T steps. It would be great if I could prove easily that my thing is going to terminate quickly and not consume too much gas. It would be great if I could prove that my thing is not going to spend too much money. It would be great if I can prove that no one can steal money from my thing. But that, I think, has a lot more to do with language design than Turing completeness. It's true that the languages that tend to be not Turing complete, depending on how they're designed, you might have algorithms that makes them easier to decide. But even something like Bitcoin, so Bitcoin script is not Turing complete. Obviously, it's a very simple script. However, I can do a simple Bitcoin program, which is pay anyone who comes up with a pre-image of that hash. That's a very simple Bitcoin script. Can anyone, but if I do that, will anyone be able to know if this contract is executable? Well, no one knows if there's a pre-image to that hash, and it would be exponentially hard to find if there is. So how is it? You could also just say, well, I'll simulate every possible input to that smart contract and see if they terminate. So in practice, it's really about how easy it is to reason about your language. Now, I'll give I'll give a counter to what I've been saying. Which is, there's a protocol called Zen protocol. And what they do is that when you submit a smart contract, you have to submit a proof of boundness, like that it will terminate in less than T steps. So why do we care about that? Because you can just use gas. Well, the thing is, then you don't have to use gas. That's the beauty of it. If you're guaranteed that your program is going to run in less than T step, you don't have to instrument your code and count the steps at every time, which is less efficient. You can just compile it and run it very efficiently because you've already convinced yourself, you've seen a proof that it would be very that you will always run in less than T step. So that's that's potentially interesting approach. But in general, I also think that executing contract is something that's going to disappear, right? Because in one model, you submit an input to a contract, and then the blockchain validator executes a contract and gets the output. But another model that would not involve any execution would be for you to just send the entire trace, execution trace of your contract. You start with the input, you execute the entire trace, you get the output, and you submit that. Now they don't need to execute any Turing complete steps. You just need to verify that every step in your trace is correct. Now that's very easy, but that's expensive because you still have to pass this giant trace. But you could get a zero knowledge witness, and you could get that in a log of the size of your trace. So let's say that we care only about programs which finish in less than 2 to the 64 steps, which is most programs we care about. You could have basically a constant size proof, a very small proof that says, okay, I executed this contract, this is the outcome. When you just send that, and then the proofs that your outcome is correct. And then if you do that, then you really don't care about Turing completeness at all. You only care insofar as, for yourself, insofar as you want to write a good contract. Yeah.
And also to rebound on this, it's also convenient to have a Turing complete language to target from. It's also a good idea to have a Turing complete language to target for compilation from a DSL that is not as well.
Yeah, no, absolutely. So you say it's a good idea to have a Turing language to target as compilation. So you can build more restricted DSLs, which are going to be less expressive and more easy to reason about. But then you can have a formally verified compiler to your language, and it'll be easier if your language can do everything. All right, Pierre? No?
Well, yeah, I have a question about the ecosystem somehow of blockchain. There is not one single blockchain, there are several updates, and I think it's also a level of decentralization which is good to have. And so my question is, well, what exists and what needs to be done so that blockchain can live in an ecosystem of them? Do you have?
So your question is, what needs to be done for blockchains to exist in an ecosystem? So I'm not.
Or to interact one with another.
Oh, okay. To interact with one another. So there are a few projects which are really focused on interoperability between blockchains. I can think of two. One is Cosmos, and the other one is Polkadot. So Cosmos is trying to create the internet of blockchains, so have many blockchains that will talk to each other. And the ways they do that is that they have this consensus algorithm, which is tenements, very close to traditional BFT agreements. And that also makes it easy to port proofs of consensus from one chain to another. So it's easier to pass state around between different blockchains. So that's one approach. The other one is Polkadot, where they just have one big blockchain. And then, so it's a blockchain that does kind of adjudication. So people run their own blockchain, and then they put hashes of their blocks, and then someone can challenge a transition. And then they have a WebAssembly version of the transition function of the blockchain, and then they show where there's an error in the trace of the transition. So it's pretty heavy machinery, but you in some sense you get a lot of sharding for free. Everyone runs their own blockchain, and then if there's any error, you go on the Polkadot blockchain and say, like, there was an error here, like that transaction was invalid, and here's why. So these are different approaches. I'm less excited about interoperability because, so why do you need different blockchains? And a reason why would be that there are trade-offs in the design of blockchain, right? If there's a way of designing a blockchain for healthcare a certain way, and then a way of designing a blockchain for lettuce another way, then you don't want to do a blockchain that does both healthcare and lettuce, because maybe you'll be bad at both. But the thing is, I think there are very few design trade-offs that exist in this space. There are solutions which are generally better in almost every dimensions you can take. So the real trade-offs that I can think of are, there's a trade-off between, that exists in any system, between liveness between liveness and safety, right? So if you want to continue at all time every time, sometimes your system might not be safe. So that's potentially a problem. And right now, the choice that most of the blockchains made, including Tezos, is liveness. You have a trade-off between decentralization and throughput. Obviously, if you want to be processing millions of transactions per second on one blockchain, you're not going to have a whole lot of people just running it on their laptops. So those are real Those are real trade-offs. I think there's also one between like how underground do you want to be versus how mainstream do you want to be. So those are real trade-offs that exist, but there's not a whole lot of other.
Okay, that was my question. Do you think there will be we need the several blockchain, or do we think?
No, I think in the future I mean, there will be a lot, but because there's a long tail for everything, right? But I think the ones that matter, I think they will be maybe I don't know, 10 years from now. I think 4 or 5.
How about other approaches like these chains, holo chains, or?
How about other projects like BizChain and HoloChain?
Yeah.
I haven't really followed BizChain and HoloChain.
And Hashgraph?
Hashgraph, I read their paper. So they tried to get common knowledge by like basically gossiping about gossiping. Like, I got a message from this one, and now I got a message and you got a message from this one, and you build a tree like this and you get consensus. The thing is like, okay, so, you know, why not? Hashgraph has a peculiarity of, I think, their stuff is patented or copyrighted, and, you know, I guess it's neat. I don't think it's what makes a difference in this environment. There's many consensus algorithms. Your consensus algorithm needs to be fast enough and it needs to work. It's a vast design space. So I don't think that it's, I don't think that having a better consensus algorithm than anyone else is going to be a killer feature when 99% of this stuff, maybe not Hashgraph, but 99% of this stuff is open source and open research.
Okay, it's 2 hours. The camera.
All right.
It's 2 hours.
Perfect. Thank you.
Hey, thank you.